Hello and welcome to Beamer Folk.
Well, this is my bird's nest on a breadboard. If you've come straight here to this video, I strongly advise you click on the link above to go to the first video explaining all, or else this probably won't make a great deal of sense to you. This chopper amplifier was a bit more of a challenge than I thought to put it onto a breadboard, but I'll come to that in a second. I'll just go through what we've got before us here, just so that we can see what we're looking at. First of all, on the left hand side we have a 555 CMOS, which is running at 5.6 kilohertz clock. The reason why it should have been 10 kilohertz, but I found with 10 kilohertz the breadboard system, with the capacitance between the terminals and the way all the wires are fly here, it caused instability. So what I did was reduce the clock frequency. It doesn't really matter to this circuit, within reason, what the clock frequency is. All that is very important here is that the two drives to the NMOS FETs are in antiphase. That is, when one's on, the other one's off, and vice versa. Okay, so we've got a 555 on the left hand side. The next IC which is in here is a 4013. That's the divide by 2. You've then got in here a very simple amplifier as described, followed by a TLO 72. There are one or two little components on the side here which are not actually in the circuit. Down here is, I've brought all the terminals out to test down to this second breadboard to stop me probing inside of this circuit. And you can see on the right hand side a digital voltmeter, and that's on the output, and at the moment it's reading 10 volts. It's reading 10 volts because the potentiometer, which is a 100k potentiometer, which incidentally I don't have stock, I've replaced with a 100k resistor, which is here, and that represents, for the reference voltage, this represents 10 volts. As compared with my Falstead circuit diagram of this chopper amplifier, there are one or two minor alterations I've made in here. In practice, this is not unusual, is it, that the real world is very slightly different to the theoretical one. But one of the things I had to do here was to put a bit of silver foil under the breadboard to help reduce cross interference noise between the various tracks and wires here. The alterations to the circuit itself, there are one or 2 points. One is I've changed the clock to 5.6 kilohertz with a timing capacitor of 2.2 nanofarad. That's inside here of the 555. And the two resistors here are 56k, which describe the astable frequency running there. Moving along, everything else is the same and correct, except for I had to place two decoupling capacitors on the TLO 70 from their respective positive and negative supply to ground. So you've got two small electrolytics. They're 210 microfarads. And that's about it as far as that's concerned. I've got on the input to the integrator, there's 120k here, and as you can see, one touch on this wire, you can see that last digit of the DVM is kicking a bit. But on the 120k here, there is a padding resistor across that of 1.5 megohm. If you built this, that would probably be a slightly different value. Oh yeah, the other thing that was wrong, this was a bit of a challenge to build. As far as an actual component that was failing, I found that the TL 431. I've had these for quite some time, maybe 4 or 5 years in stock, and the one that I used had thermal instability after 10 or 15 minutes of slightly heating up. The 2.5 volt reference would fluctuate slightly, so would oscillate between values, and that of course had a rather disaster effect on the output. The other thing I would mention is the integrating capacitor. Because I've dropped the frequency from 10 kilohertz down to 5.5 kilohertz, the integrating capacitor here I changed from a 0.1 microfarad up to a 0.33 microfarad. Of course, if you're integrating a lower frequency, you do actually need a slightly higher capacitor to get the equivalent smoothing value. This type of DSO is not really brilliantly accurate, but it's a good guide. The duty cycle is 52%, and that is the duty cycle of the 555. It needs to be as close to 50% as possible to drive the power supply, the negative supply, as good as it does. Now, the first thing I'll check is the supply voltages. So I just disconnect the DVM from the output of the DC amplifier and choose a point. Let's get that out of the way and choose a point to measure. Right, the positive supply is 14.1, say 14.1 volts DC. The negative, let's choose a negative point here, which is, say, there. And the negative value is minus 12.73. So there is, of course, a slight difference, as we discussed, between the positive and negative supply. Now I'll hook it back up to the output of the DC amplifier, and we're still at 9.999, slightly under the 10 volts, but there we are. The DSO input resistance is 1 mega ohm, and there's a small amount of capacitance on the input lead, and this affects the rise and fall time very slightly of the clock of the 555, and that can affect the rest of my test points as well. So don't be at all surprised if you see this value change as I move the DSO across the test points. Right, the first point, as you can see here, is the square wave on the trace. Here is the square wave of the clock. The next position should be a square wave that drives the first NMOS FET. And as you can see here, I don't know whether you can read this, I'll mention it. The clock frequency now has dropped to half, which is 2.77 kilohertz, and we've now got an exact 50% duty cycle, which is what you would expect if you go through a 4013 divided by 2. We're still holding at 9.99 volts. And if I move to the next pin, which is this one here, it's exactly the same. But of course, because this is not dual trace, I can't show you, but this is actually 180 degrees out from the previous trace. Again, it's reading the 2.76 kilohertz at 50% duty cycle. The next one, which is here, is, let's move this over to there. This is the reference voltage, the TL431 reference voltage, and you can see the volts per division here is set at 1 volt, and so if that's the baseline, which is here, do it the other way round just in case you can't see the black tip. So the baseline, which is here, so you've got 1, 2, 2.5 where that line is, and it is a 2.5 volt reference approximately. And in fact, when it comes to references, it doesn't really matter the exact voltage as long as it is stable at whatever it is. with good temperature coefficients as well. Let's move to the next pin and see what we've got there. Of course, the whole of this circuit would be improved for being on a printed circuit board. And as this circuit is not quite refined yet, I wouldn't commit that to a board as of yet. Now you can see that this next pin has affected the DC output reading slightly, but it has. This is the drain of the first NMOS FET, and you can see that the voltage of 2.5, spin this around, 2.5 volts here, which is reference volts, is chopped down to 0 volts via the FET. Let's move on to the next pin. Now that's shot off the screen, so let's come down here. Okay, okay, that's kind of buried in data. There is a configuration here which I can remove the data, but I can't quite remember what it is. So this is the collector of the Simple Amplifier transistor amplifier, and it's on its collector, and it's riding on a DC voltage. The signal bit that you really want and after is this flickering trace up here, but it is riding on a DC voltage with reference to 0 volts here, and that is riding 2.7 volts is the base of that trace, and the trace is running at 2, 4, 6, 7, so that's 8, 10, 11. So the top of the trace is at 11 volts, and as you can see Vmax is 11.27, and the minimum voltage, which is here, is 7.4. So you're going between 7.4 and 11.27, and that is the precision voltage that you require to be reconstructed. But of course it is sitting on top, riding on top of that DC voltage, and if you were to apply a gain of 100, the signal would be saturated in the amplifier. Right, I move along to the next trace, which is the DC output, which is there. Okay, this is DC output, and go to 5 volts. Right, at the DC amplifier output of op amp 2, you've got the 10 volts, which is described here on the DVM, and that's correct, isn't it? Because you've got 5 volts per division, you've got 2 divisions, so that's 10 volts, and it is a smooth 10 volt DC supply. There's a little bit of noise coming in here, but that is this cheap DSO producing that. Right, next, what I'll do now is I'll pretend to be altering the variable control from 100k down to 0. So we're kind of pretend that this is a potentiometer. At the moment it's set to 100k. I have here a number of fixed resistors that we can use. So let's go this one here. What is this? This is a 68k. So what we would expect if we turn the potentiometer to 68k would be 6.8 volts. So rather than unplugging the first one, I'll parallel it to begin with and then take that one out. And we got 12.2 volts. Well, that's not right, is it? And that's simply because I've actually missed the pins. There we are. Let's try that. And it's 6.83 in there. I'm not quite sure where that 0.3 of an error's crept in. It's probably partly because this is hairy and partly because there is a tolerance on the resistor itself. So both of those might be showing up in the wrong direction. So that's that one. Let's try. We've got here another resistor here of 33k. Let's see if I can get this into the right socket this time. Try that. There we are. So we've got 33K is producing 3.31. And I'll alter it down now to, this is a 12K. So that should produce 1.2 volts, which it does. And there's always a slight, as you can see, there's always a slight positive error on there, and that is simply because this is a little hairy, and you can trim it out a little bit with that resistor. But I think you get the drift of how this functions by now. If you viewed this video on its own, you'd probably find it rather bewildering, but you really do need to see the first video to make sense of this second video. Finally, how can this circuit be improved the way it is? Well, it's very dependent, this circuit as it stands, it's very dependent upon the supply voltage fluctuations in the DC supply voltage. That can be eliminated, well, certainly mostly, and I would hope totally, by a couple of things. One is that the clock itself, the 555, you would kind of like that to be more of a stable frequency perhaps, although a 555 is actually quite stable on fluctuating or variable supply voltages. But what I would like to see is the TL431 with a constant current source, so that the current through the TL431 is always at one particular current, irrespective of, within reason, how you fluctuate the supply voltage. And that would produce a very consistent precision source. The next thing is the simple amplifier, which of course this is what this circuit does. It enables you to transfer and reconstruct a precision DC voltage to a precision greater or lesser, greater voltage on the output via a simple AC amplifier. Quite a remarkable process when you think about it, but I would improve the simple amplifier by again putting a constant current load, making the transistor amplifier operate into class A and be immune from this meter, and be immune from variations in the supply voltage. I hope this has all been of interest to you. It is an unusual circuit, and I quite enjoyed exploring it, although I will say setting it up on the breadboard here was a bit more tricky, and it still is a bit more tricky than I really would like. I thought I'd finish up by showing you how I attached a SOT23 NMOSFET into the breadboard circuit. Again, a little tricky. The FET is right in the middle of this strip board here, and I managed to glue it dead bug-like onto the center strip here, and with very fine wires solder to the connections here and here to the three strips here. The first strip, which is the black one, is the source, the next one is the drain, and the third one is the gate. And of course I soldered on the appropriate little wires so I can plug it into the breadboard. And I'd like to also mention some good news in that I managed to get the clock running at 10 kilohertz. One of the contributing problem factors that I experienced on this breadboard was that I was using a power supply, which is fundamentally a switching power supply, and a small amount of that switching frequency and noise
was being delivered over the power supply wires. So I moved completely to a battery, a 12 volt, I think 12.65 volts DC battery source. So effectively it produced the cleanest type of supply. And with that, I was able to get the clock back up to 10 kilohertz. It works all completely the same. As I said, it doesn't within reason matter what the clock frequency, as long as they are, as long as there is a 50%, absolutely 50% duty cycle. So, but in the process of doing that, of course, I then had to revert the integrator capacitor back to 100 nanofarad. The timing components of the Nephi 5 ended up as a 1 nanofarad and two 6K 8 resistors, op-amp resistors, the gain resistors I changed. All of this, because there is quite a bit of change going on here, I redid the Falstad circuit diagram, the simulator circuit diagram, and called it Chopper Amp Battery Version, and that is downloadable, the link of which is in the description. Also, there was within the alteration, because it was a slightly lower voltage and this circuit, it's critical, the supply voltage, I had to make a slight change to the working point of the simple transistor amplifier. And as I said, it came up well. There's still a little bit of noise in the bird's nest itself, which I couldn't eliminate, and that is just a function of the fact that it is such a bird's nest. Anyway, in the end, I got success, and I was pleased that I achieved that. This is Beamer signing out for now.